Could climate solutions backfire into a new ice age? What if our attempts to fix the climate crisis accidentally sets off a cascade of events that turned Earth into a frozen wasteland? Could saving ourselves from global warming ironically plunge us into a new ice age instead? When we talk about combating climate change, we're usually imagining a future where Earth is livable, balanced, and free from the worst impacts of rising global temperatures. But what if, in trying to cool the planet, we overshoot our target and tipped it too far in the other direction? Could our efforts to mitigate global warming unintentionally trigger a new ice age? Before we dive into whether this is even possible, it's important to understand what exactly we're doing or planning to do to combat climate change in the first place. One of the most talked about ideas in climate science right now is something called geoengineering. Essentially, geoengineering refers to large-scale technological interventions in Earth's natural systems, designed to counteract the effects of climate change. Think of it like trying to hack the planet's thermostat. The two main branches of geoengineering are solar radiation management, or SRM, and carbon dioxide removal, or CDR. Both have the same goal: to slow or reverse global warming. But they go about it in very different ways, and both come with a hefty list of risks. Let's start with solar radiation management, SRM, the branch of geoengineering that focuses on reflecting sunlight away from Earth to cool the planet. SRM is like putting a giant pair of sunglasses on Earth. The most well-known SRM strategy is stratospheric aerosol injection, SAI. It's inspired by natural events like volcanic eruptions. When volcanoes like Mount Pinatubo erupted, they spewed sulfur dioxide into the stratosphere, creating a haze of particles that reflected sunlight and temporarily cooled the planet. Scientists suggest we could replicate this by spraying aerosols, tiny reflective particles, into the upper atmosphere. On paper, it sounds like a quick fix, but as we'll see later, quick fixes often come with big trade-offs. Another SRM technique is marine cloud brightening. This involves spraying salt particles into low-lying marine clouds to make them brighter and more reflective. The brighter the clouds, the more sunlight they bounce back into space, cooling the Earth below. It's a relatively low-tech idea compared to SAI, but it still involves tinkering with complex climate systems we don't fully understand. Then there are the ideas like covering glaciers with reflective sheets or painting rooftops white to bounce sunlight away. While localized solutions like these might not have a huge impact globally, they illustrate how focused SRM is on manipulating sunlight to cool the planet. On the other side of the geoengineering spectrum, we have carbon dioxide removal, CDR. This approach takes aim at the root cause of climate change, the buildup of greenhouse gases in the atmosphere. Unlike SRM, which deals with the symptoms of global warming, CDR is more like treating the disease itself. One of the most ambitious CDR strategies is direct air capture, which involves sucking carbon dioxide directly out of the air and storing it underground. Think of it like a giant vacuum cleaner for the atmosphere. Another method is bioenergy with carbon capture and storage, BCCS, where we grow plants that absorb CO2, burn them for energy, and then capture and store the carbon emissions. It's a potentially carbon-negative process, meaning it removes more CO2 than it emits. There's also ocean fertilization, an idea as controversial as it is fascinating. By adding iron or other nutrients to the ocean, we could stimulate the growth of phytoplankton, tiny marine plants that absorb CO2 during photosynthesis. When these phytoplankton die, they sink to the ocean floor, taking the captured carbon with them. It's a clever idea in theory, but the ecological risks of messing with ocean ecosystems are enormous. What if we accidentally create massive dead zones or disrupt marine food chains? Now you might be wondering, how could any of these methods, designed to cool the planet, possibly lead to something as extreme as a new ice age? After all, an ice age requires a massive, prolonged cooling of Earth's climate, not just a temporary dip in temperatures. But here's the thing. Many of these geoengineering strategies work by manipulating delicate climate systems that we don't fully understand. Small changes in one part of the system can have unpredictable ripple effects elsewhere. If SRM techniques like aerosol injection were overused, for instance, they could reduce global temperatures far beyond what we intended. And if we cool the planet too much, we might set off feedback loops that could spiral out of control. To understand why this is such a big deal, it helps to think of Earth's climate as a finely tuned orchestra. Every instrument, ocean currents, atmospheric circulation, ice caps, vegetation, has a role to play in maintaining the planet's overall balance. If you mess with one instrument, say by injecting aerosols into the stratosphere, others might go out of tune, creating a cascade of unintended consequences. And that's the real danger with geoengineering. It's not just about whether the technology works, but whether we can predict and control its side effects. For example, stratospheric aerosols could cool the planet but also disrupt precipitation patterns, leading to droughts in some regions and floods in others. They could also weaken the Asian monsoon system, which millions of people depend on for their water supply. On top of that, aerosols might damage the ozone layer, exposing life on Earth to harmful UV radiation. And if we ever stopped using SRM abruptly, say due to political or economic reasons, we'd face a phenomenon called termination shock, where temperatures rebound rapidly, causing even more chaos. So while the idea of hacking Earth's climate to save ourselves from global warming might sound like a sci-fi dream, it's a risky game to play. The stakes are incredibly high, and the margin for error is razor thin. As we'll explore in the next section, history offers some chilling examples of how sudden cooling events have reshaped the planet in the past. Could our modern inventions accidentally trigger similar outcomes? When we think about Earth's climate, we tend to imagine it as a steady, self-regulating system. But in reality, it's more like a precarious balancing act, where a slight nudge in the wrong direction can send the entire system spiraling into chaos. This is the concern with large-scale interventions like geoengineering. While the goal is to stabilize the climate and counteract global warming, there's always the risk of overcorrection. Could our efforts to cool the planet go too far and throw us into a new ice age? To answer that, we need to dive into what happens when cooling goes wrong and how even small disruptions can cascade into global consequences. One of the most alarming risks of geoengineering, particularly solar radiation management (SRM), is the possibility of excessive cooling. Imagine if we were to inject an enormous amount of aerosols into the atmosphere to reflect sunlight. If we miscalculated or overshot the amount needed, we might end up cooling the planet far more than intended. This isn't just theoretical. Scientists have modeled scenarios where excessive SRM interventions could reduce global temperatures so drastically that they could mimic the cooling effects of major volcanic eruptions, except on a longer, more sustained scale. The consequences of such an overcorrection could be catastrophic, as rapid temperature drops could destabilize ecosystems, disrupt food production, and trigger feedback loops that make the cooling self-reinforcing. But what exactly are these feedback loops, and why are they so dangerous? Earth's climate system is interconnected in ways we're only beginning to understand, and cooling one part of the system can set off a chain reaction. For example, if temperatures drop significantly, the planet's ice and snow cover might expand. This would trigger something called the ice albedo feedback loop. Ice and snow reflect sunlight much more effectively than land or water, so the more ice there is, the more sunlight gets reflected, and the cooler the planet becomes. This cooling in turn leads to even more ice formation, amplifying the effect. It's a runaway process that could potentially spiral out of control, pushing the planet into a state of prolonged cooling. Could something as drastic as an ice age be triggered this way? Well, it's unlikely in the short term. The potential for significant and lasting cooling remains a serious concern. To better understand how this might play out, let's look at some historical examples of abrupt cooling events. One of the most famous is the Younger Dryas, which occurred about 12,900 years ago. During this period, global temperatures dropped sharply, especially in the northern hemisphere, plunging parts of the planet back into near glacial conditions. Scientists believe this cooling was caused by a disruption in the thermohaline circulation, the system of ocean currents that transports heat around the globe. The disruption was likely triggered by a massive influx of fresh water into the North Atlantic, possibly from the sudden melting of ice sheets. Fresh water is less dense than salty ocean water, so it interfered with the sinking of cold, salty water that drives the circulation. The result? A dramatic cooling of the North Atlantic region that lasted for over 1,000 years. Now let's connect this to geoengineering. Some SRM techniques, by altering precipitation and temperature patterns, could also disrupt ocean circulation. For instance, cooling the planet too quickly might lead to changes in rainfall, causing more fresh water to accumulate in the North Atlantic. This could weaken or even shut down the thermohaline circulation, much like what happened during the Younger Dryas. If that were to happen today, the consequences would be devastating. Europe would experience severe cooling, while other regions, like parts of Africa and Asia, might face catastrophic droughts. A disrupted ocean circulation system would also affect marine ecosystems and fisheries, which millions of people depend on for food and livelihoods. Another historical example of abrupt cooling is the Little Ice Age, which occurred between the 14th and 19th centuries. This period saw cooler global temperatures, leading to harsher winters, crop failures, and even societal upheaval in some regions. While the exact causes of the Little Ice Age are still debated, factors like decreased solar activity and increased volcanic eruptions likely played a role. The volcanic eruptions injected aerosols into the atmosphere, which reflected sunlight and cooled the planet, much like how modern SRM techniques aim to work. The key takeaway here is that even relatively small changes in atmospheric conditions can have outsized effects on global temperatures and human societies. But it's not just the cooling effects of geoengineering that we need to worry about. It's also what happens if these interventions are suddenly stopped. This brings us to the concept of termination shock. If we were to rely heavily on SRM to keep the planet cool and then abruptly halt those efforts due to political instability, funding issues, or other reasons, global temperatures would rebound rapidly. This is because, unlike CDR techniques, SRM doesn't actually remove greenhouse gases from the atmosphere. It just masks their warming effects. Stopping SRM would expose the planet to the full force of accumulated greenhouse gases, leading to a massive and sudden rise in temperatures. Termination shock wouldn't just undo the cooling achieved through SRM, it would likely overshoot into extreme warming, wreaking havoc on ecosystems, economies, and human health. So, what's the solution? How do we counteract global warming without risking overcorrection or creating new problems? That's the billion-dollar question. Scientists emphasize the importance of using geoengineering as a last resort, not a primary strategy. The focus should remain on reducing greenhouse gas emissions and transitioning to renewable energy sources, which address the root cause of climate change without the risks associated with large-scale interventions. But even with these precautions, the ethical and governance challenges of geoengineering loom large. Who gets to decide on how much cooling is enough? Which regions or populations might bear the brunt of unintended side effects? And how do we ensure that these technologies aren't misused or weaponized? What do you think? Should humanity even consider geoengineering as a solution to climate change? Or is it too risky to tamper with such complex systems? Let us know your thoughts in the comments. Now that we've explored how climate interventions like geoengineering could potentially cause unintended cooling and even disrupt delicate systems like ocean currents, let's dive into the big question. Could these efforts actually provoke something as extreme as a new ice age? Ice ages are monumental shifts in Earth's climate, driven by natural mechanisms that occur over thousands or even millions of years. So how does this compare to the rapid, human-made interventions we're considering today? And are we truly at risk of inadvertently triggering such a dramatic freeze? To answer this, we first need to understand what drives natural ice ages in the first place. The primary mechanism is tied to Milankovitch cycles, which are slow, predictable changes in Earth's orbit tilt and wobble. These cycles affect how much solar energy reaches different parts of the planet over tens of thousands of years. When conditions align, such as a reduced tilt of the Earth's axis or an elongated orbit, less sunlight reaches the higher latitudes, allowing ice sheets to grow and cooling to intensify. This triggers a cascade of feedback loops, like the ice albedo effect we mentioned earlier, eventually leading to an ice age. The last major ice age, known as the Pleistocene glaciation, ended about 11,700 years ago and left behind the vast ice sheets that once covered much of North America and Europe. On the other hand, what we're dealing with today is fundamentally different. Human-made climate interventions, like geoengineering, act on much shorter timescales, years or decades rather than millennia. Unlike Milankovitch cycles, which are gradual and natural, geoengineering is rapid, deliberate, and often unpredictable. This raises an important distinction. While the likelihood of triggering a full-scale ice age through current geoengineering efforts is low, the risk of causing localized or temporary mini-ice age conditions is much more plausible. For instance, if solar radiation management (SRM) techniques were to cool the planet too quickly or unevenly, certain regions could experience dramatic drops in temperature. This could mimic the effects of past sudden cooling events like the Younger Dryas or the Little Ice Age, even if it doesn't result in a full-blown ice age. But here's the catch. Geoengineering doesn't operate in isolation. It interacts with the planet's existing climate systems, which are already under immense strain from global warming. One key factor that complicates things is greenhouse gas levels. Historically, ice ages have been associated with low atmospheric CO2 levels, which allow cooling to persist and intensify. Today, however, CO2 levels are at record highs due to human activity. This makes it much harder for an ice age to take hold, even if we were to drastically cool the planet through geoengineering. In fact, some scientists argue that the sheer volume of greenhouse gases in the atmosphere acts as a kind of insurance policy against a new ice age, though it's hardly the kind of insurance we want to rely on. That said, there's another layer of complexity: the potential for geoengineering to disrupt natural climate systems in ways that are hard to predict. For example, if SRM were to significantly alter temperature and precipitation patterns, it might impact the thermohaline circulation, the system of ocean currents that helps regulate global climate. A shutdown or slowdowns of these currents, as we saw during the Younger Dryas, could plunge regions like Europe into severe cooling, even if the rest of the planet remains relatively warm. Similarly, large-scale interventions could trigger unexpected feedback loops in the Arctic or Antarctic, where ice dynamics are already highly sensitive to temperature changes. In other words, while we might not induce a global ice age, we could create regional conditions that feel eerily similar. So, what does the science say about all this? Fortunately, most climate experts agree that the risk of provoking a full-scale ice age through geoengineering is extremely low, at least with the techniques currently being proposed. Ice ages require a unique combination of factors, like reduced CO2 levels and long-term changes in solar radiation, that geoengineering simply can't replicate. However, the risks of unintended cooling, regional disruptions, and feedback loops remain very real. This is why many scientists advocate for extreme caution when considering geoengineering as a solution to climate change. Without comprehensive research and robust international oversight, the potential for unintended consequences is simply too great. But there's also a deeper, more philosophical question at play here. Should we even be tampering with the planet's climate systems at all? Geoengineering represents a level of technological intervention that borders on hubris. While it's tempting to think we can hack our way out of a climate crisis, the reality is that Earth's climate is an incredibly complex, interconnected system. Every action has a ripple effect, and we're far from understanding all the ways in which those ripples might interact. Even with the best intentions, we could end up creating new problems that are just as severe, if not worse, than the ones we set out to solve. So where does that leave us? The most effective and least risky way to combat climate change remains the same: reducing greenhouse gas emissions. This means transitioning away from fossil fuels, investing in renewable energy, and protecting natural carbon sinks like forests and wetlands. While geoengineering might have a role to play as a last resort, it should never be seen as a substitute for addressing the root causes of the problem. After all, the goal isn't just to stabilize the climate, it's to create a sustainable and equitable future for everyone on the planet. If you found this exploration thought-provoking, don't forget to like the video and hit that subscribe button for more deep dives into the big questions about our planet and beyond. And as always, stay insanely curious.